Okay. Sorry for bit delay. Some meeting going on. Anyway, so I was looking at different codecs. I mean the basics of the codecs, and especially we started with cyclic code. I'm just recalling what was a code. So a code is nothing but linear code is nothing but a k-dimensional subspace of a vector space of length n, right? Over binary field, we'll call it binary code, or if it is a field with q number of elements, it's called as a query code, right? Now, so we looked at how do we encode the data. So there are two ways to encode the data. Since linear code is a subspace, one can have a generator matrix and a parity check matrix representing the code C, and from G, so if there are k bits, we multiply with G, which is k by n, gives you n bits. So k bits are converted into n bits to encoding, and similarly, with the help of parity check matrix, if you want to do encoding, so we take k bits, we add extra n minus k bits such that hx transpose is equal to 0. Right? That is a way of constructing the code encoding. Now, decoding I talked about in the last class, three kind of decoding. First was sphere decoding, right? So you draw the spheres around each code word in C, and if the minimum distance of the code is d, we know that the radius of the sphere is d minus 1 by 2, right? So these are disjoint spheres, so we are able to decode nicely. And the other second decoding method was coset decoding. You form a coset kind of thing, array, and then you send something from C, X, receive Y. It will be in one of the coset, whatever coset it is. Choose the coset leader, subtract it, and you will be able to decode it. Right? That's a standard method. And third method is syndrome decoding. So once you send X from C, Y is received with T errors. So then what you do is just compute the syndrome of Y, which is HY transpose. And syndrome is one of the column, right? Depending on where it is, and you are able to decode it, right? So basically, if there are single bit error, syndrome is nothing but one of the column in the parity check matrix. If there, suppose the error is at third and fifth position, it will be the sum of the columns at third and fifth position in the parity check matrix, right? So that is how syndrome represents where the errors are actually. So, and I think I have shown you the basic idea of Hamming code, right, which can correct single bit errors, and it was the decoding of Hamming code is really simply because very straightforward. Because distance is 3, so we need to basically it can correct single bit error, so t is equal to 1, right? So in the case of Hamming code, uh, you know, if x is sent from as a vector from Hamming code, y is received, one bit is in error, you just compute the syndrome, it will be one of the column in the parity check matrix, right? And whatever column position it is, just flip that position in the received vector and you will get x. That is the decoding in the Hamming code. Now, Hamming codes are also beautiful, just like repetition code. C is equal to 0000111. That code is beautiful. Why it is beautiful? Because if you draw the spheres around each code word of radius t, t is equal to d minus 1 by 2, they cover the whole space. Right? So it's a perfect code. Okay. Second example is the Hamming code. So I leave it as an exercise for you to check that the Hamming code, and I think the parameters are 2 raised to m minus 1. Here somewhere we must be, yes. Yeah. So length is 2 raised to m minus 1. Dimension is 2 raised to m minus 1 minus m, and the distance is 3. So with these nkd parameter of a Hamming code, now for each, now you can verify this, for each code word x in the Hamming code, if you draw the sphere of radius t, t is equal to 1 here, because d is 3. So 3 minus 1 by 2 is 1. Okay. So if you draw the spheres of radius 1, they will cover the whole space. So these are also beautiful codes, perfect code. And third example is the Gole code, which we'll talk about later on. So actually, somehow, see, if something is beautiful in the nature, it is always related to some other beautiful thing. So from one beauty, you can find another beauty. Same thing happens with these codes. All these codes are related somehow. So basically, from Hamming code, you can do some. So basically, take some beautiful thing and you can convert. So there are ways, where things can be connected. Anyway, so that's all about Hamming code. Now, This encoding and decoding can be even more simplified when we use a special kind of structure in the code, which is known as cyclic code. Okay. So what is a cyclic code? First of all, it should be a linear code. Linear means it should be, subspace. Means if x and y are two vectors, linear combination is also in C. So x plus y is in C, right? So that's a linear code, which is okay. Number one. Number two, any cyclic shift of a code word is again a code word. You take a code word. So for example, this is a nice thing. If you look at this code, obviously it's a linear code because if you take any two vectors which are linearly independent, they will give you all four vectors, right? If you take any two vectors as a basis, it will give you all four vectors. This code is a cyclic code. Why? Because if I take 0, 0, 0, I take a cyclic shift, again you are in the set. Take another shift, you are again in the set, right? Even for this one. 1, 0, 1, shift is 1, 1, 0. So you will get that vector, right? If you take 1, 1, 0, take a shift, you get this vector, right? So take any vector in the set, it's closed with respect to cyclic shift. Set is closed with respect to cyclic shift and it is linear. Means sum of any two vectors is also in the C. So such kind of code is known as cyclic code. Right. So now there are some other interesting facts about it. So basically, how do we handle cyclic code? So right now it's in the form of vectors, but because of this cyclic nature, you will see that you can represent them as a polynomials, and polynomials are means we can bring some algebraic machinery of polynomial rings, and then it becomes very easy to handle. Let me show you some examples. So now, before that, if you look at this example here, 0, 0, 0, 0, 1, 0, 0, 1, 0, 1, 1, 0, and all 4, 1. So the question is it a cyclic code? So with respect to 0 vector, we know it will be there always in the C. If you take shift, no issue. What about 1, 1, 1, 1? If you take shift, again it will be in the set, no problem. What about 1, 0, 0, 1? If you shift, you will get 1, 1, 0, 0, which is not there in the C. Right? So it is not a cyclic code. Got it? This example here is not a cyclic code. But you can do certain column transformations and you can make this code to be cyclic. So what I am going to do, for example, if you look at this, what I am doing here, can you tell me what kind of column transformation I have done? So I'm just shifting. So you write down basically all vectors as an array, first vector, second vector, third vector, fourth vector, and apply some column transformations, bitwise, column. So what will happen? So what is this actually? If third and fourth column, if you swap, right? So no, not third and fourth, right? Okay. Yeah. So if you just swap third and fourth column, you will basically get this vector, right? I mean this is this code, and now you see this is a cyclic code because this is closed with respect to cyclic shift. If you take this vector, take a cyclic shift, you are again here, right? Everything is satisfied, and also if you take the sum of any two, you will get all the four. So that property remains same, right? So sometime by column permutations, it is possible to make a non-cyclic code into a cyclic code. Okay, that is a beautiful thing. What about this code? Is it a cyclic code? 1, 1, 1, 1, 1. Any idea? Is it a cyclic code? Well, this vector is, if you take the cyclic shift, no matter how many times you remain in the set. So it is closed with respect to cyclic shift. But this is not a linear space. 0, 0, 0 vector is not there. Subspace, the linear code is the number one property, right? So 0, 0, 0 vector should be there, which is not there. So this is not a cyclic code. What about this code? All 0 vector. All 0 vector is a trivial subspace, right? So it is a linear code. And if you take the cyclic shift, it is also closed with respect to cyclic shift, right? So this is also, yes, this is a cyclic code. What about this? Lambda times 1. So where lambda is any element in field with few number of elements. So 0, 0, 0, 0, 1, 1, 1, 1, 1, right? And like that, lambda, all scalars. So if you take any vector, you take the cyclic shift, you are again in the set. So, and also it's a linear, generated by all one vector, right? So it's basically it's a cyclic code. Similarly, whole space is also a cyclic code, SQN. I have given you enough examples of cyclic and non-cyclic code. So cyclic code means two conditions: should be linear code, number one. Number two, it should be closed with respect to cyclic shift of every vector. Right. So these two properties are there. Now you see, now I'm going to show, yes. Hmm? No, yeah, so basically lambda is a scalar. So it is saying that first vector is, so when lambda is 0, the first vector is all 0 vector. Right. When lambda is 1, you will get all 1 vector. When lambda is alpha, I mean, FQ, power of alpha will be there in all elements. So if alpha is alpha, 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 right. Next vector is alpha square, alpha square, alpha square, like that. Right. And since this is generated by all one vector, because scalar is lambda, actually everything is set there. Now I am going to show you the beauty actually, right? The real beauty. Now you see, I will take these vectors and I will make polynomials. This is known as human cleverness, right? How the clever idea of converting vectors into polynomials makes your job very easy. So let us see that. So what I am going to do, I take this vector C0, C1, C2, Cn minus 1, right? And I'm taking these as a coefficient of a polynomial. C0 plus C1x plus C2x square plus dot 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 Cn x raised to n minus 1, right? I'm just converting. So this is kind of association. Each vector take the coefficient as a coefficient of the polynomial, right? So it is C0 plus C1x plus C2x square and so on, Cn x raised to n minus 1. I call it some polynomial C of x, right? Now, remember, cyclic code has two properties. It should be linear, of course. And second is that cyclic, it should be closed with respect to cyclic shift. So that means, what do you mean by cyclic shift? If I take Cx, multiply it with x, means what? Actually, we are doing the cyclic shift, right? C0, which was the coefficient, constant coefficient, is now coefficient of x, right? C1, which was the coefficient of x, now it will be coefficient of x square. Because we are, just multiplying x, everything is shifting, right? Only thing we need to worry about the last coefficient. Here, previously it was x raised to n minus 1, and now it is x raised to n because I have multiplied with x. Everything is shifting, right? Now, yeah, x raised to n, right? Because the top is x raised to n minus 1. I am multiplying everything in Cx by x. X times Cx is x times C0 plus x times C1x plus x times C2x square plus dot 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 x times Cn x raised to n minus 1. Right? Hmm? Oh, yeah, Cn minus 1, yes. Sorry, that I can actually. Cn minus 1, right? Fine. Okay, so now what happens? So the last coefficient should be, now it is x raised to n. In order to make sure that everything makes sense in the cyclic shift, x raised to n should be 1. Then only it will work, right? So that condition comes naturally, that x raised to n is equal to 1. So that means whenever we are doing any operation between these polynomials, we need to make sure that x raised to n is equal to 1. We need to, whenever there is coefficient x raised to n, it should be 1. Now you see the beautiful thing here. I am taking Z23, our well-known space Z23. I can write down all the 8 vectors here, right? All 8 vectors here. 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, 1, 0, 0, 1, 1, 1, 0, 1, and 1, 1, 1, right? And I associate the polynomials. So 0, 0, 0 will be obviously 0 polynomial 0 plus 0x plus 0x square and so on. 1, 0, 0 will be 1 plus 0 into x plus 0 into x square. 0, 1, 0 will be 0 plus 1 into x plus 0 into x square, right? So that is second polynomial x, then x square, then 1 plus x plus x square, 1 plus x square, and 1 plus x square. So the highest degree is 2. I am just mapping all 8 vectors of the space, whole space, I am mapping into a polynomial. So this polynomial, this collection of these polynomials we call Z2 square bracket x, known as polynomial ring. Okay, I am not sure if you have done a course on algebra, but probably not, right? But anyway, doesn't matter. We are doing only fun things right here, all examples, so you can see what is happening. See the beauty. So we have all these polynomials, 8 polynomials, right? Now, first of all, if I take 1 plus x and x plus x square, add them as a polynomial, what will happen? 1 plus x plus x plus x square, that is 1 plus 2x plus x square, but 2 is 0. Everything is modulo 2, so you are left with 1 plus x square. So is it happening as a vectors? So that means this plus this gives you this, right? Now what happens here? If you take this, sorry, this plus this is what? 1, 0, 1. You get this vector here. See how nicely everything is matching, right? I am just adding with coefficients modulo 2, and I am actually getting in the same manner as vectors are added, right? Right? This is what is happening. You can take any sort of thing. So basically, with respect to addition, we know how to add the polynomials. Now, if we multiply, what will happen? Now, one thing, first of all, whether this is a cyclic code, this whole space is a cyclic code anyway, right? You take any vector, you take shift, it is there, right? And also it's a linear. You can find 3 vectors, say for example, 1, 0, 0, 0, 1, 0, and 0, 0, 1, that will span the whole 8 vectors, right? This is a whole space is always a cyclic code, right? Trivial code. Now, out of these 8 polynomials, suppose I take 1 plus x, and now I multiply with x, what will happen? X plus x square. So we are getting this, and that is true because 1, 1, 0 is shifting 0, 1, 1, right? The cyclic shift things are preserved. So if we take a polynomial, multiply with x, we are shifting it once. If we multiply with x square, we will be shifting it twice, right? That property will remain same. So I think if I take, so okay, suppose take 1 plus x square and multiply with x, what will happen? X plus x cube. But x cube is not there because x cube should be 1 because everything is the highest power is 2 here, right? So 1 plus x square, when we multiply with x, it is x plus x cube. X cube is 1, so this is x plus 1. What is x plus 1 means? Which is this, right? So when we take a shift, we are actually getting this. Yeah, that condition is the only thing. When we are multiplying, we need to keep that thing in mind that x, no, x is not a 0 or 1. X is basically just intermediate value in a polynomial. We are only worried about the coefficients of the polynomial. I'm not worrying about anything else. No. I'm saying that whenever the power of x is more than 2, we reduce it to 1. So x cube is 1. That's the only thing. That's a manipulation. I'm not worrying about value of x. I'm not looking at value of x. I'm saying x is intermediate value. So I write x. So I'm saying whenever we are multiplying. So whenever we are multiplying 2 polynomials, so let us multiply this 1 plus x and x plus x square. What happens? If you multiply 1 plus x and x plus x square. I am not worrying about anything about x. It's just a symbol. You can think like a symbol. So what is happening here? 1 plus x. Sorry. X plus x square plus x square plus x cube. Right? X square plus x square is 2x square, which is 0. And x cube is 1. So this is nothing but 1 plus x. So basically, I can play. Now I have the algebraic rules to play with these polynomials. So whenever we are taking two polynomials, we can add them and just worry about the coefficients. I don't have to worry about the powers of x when we are adding. With the corresponding powers of x coefficients, we are adding modulo 2. We are done. And when we are multiplying, we need to keep in mind that x cube is always 1. You need to place, and coefficients are evaluated modulo 2. That's all. So anywhere there is a 2, 2 times x, 2 times x square, or 2, it will be 0. Right. This is a simple algebra. Right. Simple algebra, we are playing with it. Right. Any question at this point? This example is really nice. Any question about this point? Easy to understand? Just playing with polynomials. Now, remember that code C is equal to 0, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1. That's a cyclic code. Remember? It is a cyclic code we just saw. Because both the two properties are satisfied. It's a linear code. It's a dimension 2, 1, 1, 0, 1, 0, 1. You can take as a basis, right? And it close respect to cyclic shift. You take 0, 0, 0. You are again in the same set. 1, 1, 0 will give you 0, 1, 1, right? It's closed. So this is a cyclic code. Okay. So this is a cyclic code. Now, basically, each of these things can also be converted into polynomials. I'm just writing what we are getting here. C, or I will call it I, for the reason it will be clear to you. This will be a 0 polynomial. 1, 1, 0 is 1 plus x. 1, 0, 1 is 1 plus x square, and 0, 1, 1 is x plus x square. Corresponding polynomials I have written. Now, these polynomials have certain properties. Okay, so these polynomials have certain properties. 1 minute. Okay, what are these properties? You can see that if I take an element from these polynomials, okay, take any polynomial out of these 8 polynomials and multiply it here, what you are going to get. Suppose I take 1 plus x square. So what will happen? This will be 0. First coefficient will be 0. 1 plus x square. I have taken 1 plus x square. So 1 plus x square into 1 plus x is how much? Huh? Sorry. X plus x square. You are getting this. No problem. Multiply this 1 plus x square with 1 plus x. What we are getting? We can compute. Huh? So 1 plus x square into 1 plus x square means what? I can let me compute it for you. So 1 plus x times C. 0. 1 plus x whole square is 1 plus x square. Fine. Right. Okay, I have taken 1 plus x. No problem. Anyway, no problem. That's the same thing. Next, 1 plus x into 1 plus x square is how much? One plus x square plus x cube. This is 1. So this one goes, you are left with x plus x square. Right? And the last one, 1 plus x into x plus x square. So 1 plus x into x plus x square is how much? Huh? X plus x square will be there, plus x square plus x cube. So if this goes off, you are left with x plus 1. Right? So you are left with this. You see, no matter which polynomial I take, I multiply with elements in C, we are getting the C itself. Right? This is a beautiful property. Any element in the whole space you take, multiply with every element in the subspace, we are getting the same set of polynomials. Right? Okay? This is something we can call it, if we treat our whole space as a scalars, is closed with respect to scalar multiplication. And also if you take two polynomials, add them, you are again in the set. So essentially, in terms of polynomials, so this property is known as ideal. This such kind of set in polynomial ring is known as ideal. So basically that's why this name capital I, ideal. This is a nice term, and formally this is the thing. If R is a ring, right? So any non-reducible subset of it, this is a formal definition. Anyway, I have to tell you the definition, but anyway, I told you with the examples what is happening. R is an ideal if A plus B, A minus B belongs to I for every A, B in I. I mean, A minus by here is same thing as A plus B. So that's not a problem, right? It's only one operation you need to check, A plus B. And R times A belongs to I for every R in R, for every A in A, I. Capital R ring is our whole polynomial, all 8 polynomials Z2X, right? I have taken element of Z2X, multiply with element of, from I, we are actually getting set in an element in I itself, right? So close with respect to scalar multiplication and close with respect to addition. Right? So such kind of set is known as ideal. So that ring that I have written 8 polynomials is denoted by Z2X modulo x cube minus 1. X cube minus 1 means, because remember x cube minus 1 is equal to 0, means x cube should be 1. Okay, so it is saying that whenever there is x cube, it should be 1. Okay, so this, in terms of this whole thing, is represented by R3, known as right, R3. In general, we can write it like Z2X modulo x square minus 1. We call it as a polynomial ring Rn. Okay, and so you can clearly see that this set C or I, which is 0, 1 plus x square, x plus x square, is ideal in R3. We just saw that. Take any element from the ring, I mean the polynomial ring Z2X, multiply with any element of I, you will get this closed with, right? Get the same thing, right? So this is what it is. Now, one thing I should mention to you here, what is happening? If you remember or recall the course on discrete math at some point of time, if we divide this whole ring Z2X with this polynomial x square plus x plus 1 is equal to 0. Remember, we use this polynomial to construct field with 4 number of elements. Remember, x square plus x plus 1 has no root in Z2, right? And then we use it to construct field with 4 number of elements Z of 4. And how will we form these tables, right? Addition and, here x, you can also call it in terms of alpha. If you remember, alpha is the root of x square plus x plus 1 is equal to 0, and those things you recall. So you can actually, important thing what I want to tell you, if this polynomial, modulo polynomial that we are taking is irreducible over the ground field, here because x square plus x plus 1 has no root in the ground field, when you do this operation of modulo, you get a field, whole space you get field, because field means, every element here, has a additive inverse, and also with respect to when you make the multiplication table, it will be, every non-zero element has an inverse with respect to multiplication. Those two properties holds here. Okay, so this is a field. When the modulo polynomial that we are taking here should be, if it is irreducible. Now, in our case, what is happening? Here Z2X, our condition is x cube minus 1 is equal to 0, right? So that modulo polynomial has a root x equal to 1. So actually that polynomial is not going to give you field, but rather ring. And that is what is happening here. You see. Another example is, suppose we take x square plus 1 is equal to, Z2X modulo x square plus 1. So actually you are getting only these 4 polynomials, 1x, 1 plus x, of course. With respect to addition, you will have 0 also. You can add, make a table. With respect to multiplication, you will see I am getting an element 1 plus x. When you multiply with 1 plus x, both are 1 plus x is non-zero, but when you multiply, you will get 1 plus x square, but 1 plus x square is equal to 0 because x square plus 1 is equal to 0. So essentially, if the polynomial that we are using to build the structure is irreducible, we will get field overall. If it is reducible, means there is a root, the ground, we are going to get ring. So our polynomial ring, so Rn is a ring. The reason is that because we are taking a reducible polynomial x raised to n minus 1, right? The modulo operation we are doing with. I am giving you very basic examples just to understand what is happening. वैसे ये सब theorem के form में होता है ना, theorem proof. I don't care about theorem proof, right? We only do the examples to understand what is happening, right? Any question at this point? So basically, if you take any collection of polynomials and reduce it to modulo irreducible polynomial, you will get field. If you reduce it to modulo any reducible polynomial, you will get ring. Ring is a generalization of field. For example, in field you have this property, if the product of two numbers is equal to 0, one of them has to be 0. But in ring that is not the case. There may be two elements, both are non-zero, but their product is 0. For example, Z4, if you remember, Zn is a field if and only if n is a prime number. But Z4 is not a field because 2 into 2 is equal to 0. It's a ring. It's a general structure. Okay. So here, if we take x square plus 1 as a polynomial, which reduces every polynomial, we are going to get a ring. Okay, because now this element 1 plus x is there. So 1 plus x into 1 plus x is 1 plus x square. Basically, it is 1 plus x whole square, which is 1 plus x square plus 2x. 2x is 0, so you are getting 1 plus x square, right? And 1 plus x square, because x square plus 1 is equal to 0, you are getting reducible polynomial, right? So basically, you are getting overall structure is a ring. You can see that there is the element 1 plus x. So 1 plus x into 1 plus x is equal to 0, although 1 plus x is non-zero, right? This happens in the ring. In case of field, this will never happen. So if we take the polynomial x square plus x plus 1, actually we are getting a field. Okay? So that means you will not find two elements, their product is 0 and none of them is 0. This cannot happen in field. In field, if two numbers are there and their product is 0, then one of them has to be 0. Okay, that's a very, very basic, crude definition. And what is field? I think I'll just recall you what is field. Field where we can play with all the four operations: addition, subtraction, multiplication, division. Field is a collection of numbers or collection of anything, right? Where we can play with all the four operations: addition, subtraction, multiplication, division. All operations are possible. That is a field. Field, cricket field, football field. We can play cricket, we can play football. Number field is where we can play with numbers. All the four operations. That's a very loose, simple definition to understand. And that is enough, right, for you to understand what is happening there. So I think that's all about. You can also, I'll just summarize that any ideal here is related by a principal polynomial. I mean, let's call it as a it's a generator. 1 plus x is acting as a generator. Take 1 plus x, multiply with every element of z2x, you will get all four elements. Okay, so this is acting as a generator here. It's known as generator polynomial. Okay, so maybe I think I will come back to this again and I'll summarize something about the cyclic code basic things in the next class. And then we are going to build, I will give you, then we'll start with the DNA storage channel actually. This much is enough. Okay, fine. Thank you.